Last time we discussed some of the math of interference in one dimension. We talked about the phase being really the key quantity that determines how different waves propagating in one dimension interfere. So when the difference between the phase, which is really the argument of the sine and or cosine, which we use to describe the wave, when the phases are the same or differ by multiples of 2 pi, we get maximally constructive interference. When the phase difference is pi plus a multiple of 2 pi or some odd integer multiple of pi, then the waves are completely out of phase. So when one is positive, the other one is negative with the same value, the same absolute value, and they completely cancel out. So that gives rise to destructive interference. So a good example or a good application of these ideas is something called anti-reflecting thin film. So it's used quite a bit in optical industry. Like many eyeglasses even have that. There's a coating that reduces reflection. So let's try to understand this better. So let's say application of 1D interference. So suppose we have, let's say, a piece of glass here with index of refraction Ng, and there's a film of some other material with, let's say, NF and film. And here we have air or vacuum. Well, N is almost 1. So if you shine light on this system with wavelength lambda, then lambda is c over f, the frequency of the light you shine on it, and c is the speed of light, let's say, in vacuum, which is similar to the speed of light in air because n is approximately 1. So we kind of want to engineer the thickness of this film. Let's call it D, such that reflection is suppressed, so we don't get reflection. All right, so how can we do that? Well, the idea is, as you shine light on this, some of the light gets reflected at this interface here, right? And a lot of it goes through. So, but then some of it gets reflected from this interface here between the coating or the film and glass, and then this comes back as well. So if we manage to find the thickness such that this and this, the wave coming from the reflection of the original incident wave on the first interface is out of phase with this one, the wave coming from the secondary reflection from the interface between the film and the glass, then outside they're out of phase, so the electric and magnetic fields cancel out and it's going to be no amplitude. It's going to be dark, so it doesn't get reflected. You can kill the reflection. So how can we do that? Well, we have to think a little bit about what happens to the phase, right, as you propagate. So the key mathematical thing, remember, let's say the incident one here, we can write it as A sine kx minus omega t plus some constant. So we have to see how the the phase, which is this thing, the argument of the sign, changes as the light travels, and then what is the difference between the phase for this wave being reflected from the first interface and this wave being reflected from the second interface. Okay. So remember we talked about this example of maybe you had a thin rope and there was a thicker rope, and we sent in, let's say, a pulse. Some of it goes through, some of it gets reflected. We discussed this phenomenon where when the speed is slower on the other side, the reflected pulse or the reflected wave is also inverted, right? So inversion is a phase shift pi, right? Because you have, let's say, sine of theta is minus sine theta plus pi, right? So any sine function, let's say here you have the sine of theta for some angle, then you add pi, you go on the other side, and both its sine and cosine get a negative sign. So mathematically, the fact that the reflected wave is inverted, we can describe it by adding a phase shift of pi. So basically the incident, right, and the reflected at the interface will have a phase difference of pi. Okay, so if you want to think about the phase at some point here between this reflected one and the secondary reflection, we have to see what's happening. So first, NF is definitely larger than 1, right? It's some material, so yeah, so the speed is going to go down. And remember, n was the speed of light traveling in that medium divided by the speed of light in... Sorry, n is the speed of light in vacuum divided by the speed of light in the medium. So if the speed of light in the medium goes down, which it has to, then n is larger than 1. All right, so then we should consider two different cases, right? So NG and NF, depending on how they compare. So let's consider the case NF is larger than, or let's consider first the case NG is larger than NF. So this material used in the coating has an index of refraction that's smaller than the index of refraction of the glass. So then, here for this reflection, we have a phase shift of pi because it's reflected. Here as well, at this point, we're going to have a phase shift of pi, right? Then, apart from these two phase shifts, this one that's reflected travels this distance d here and a distance d coming back. So when it wants to interfere with this reflected at this point or somewhere later, but somewhere later, they will have traveled the same distance, so that gives the same phase shift. So the difference in phase originates from 2d, right? A difference in distance of 2d between these two waves, the first reflection and the second reflection. So if I want to write the phase difference between these between two reflected waves, let's call this 2 and call this 1. So let's call this just the interface phase shift, right? So the total phase difference, for this we get 2d times 2 pi over lambda f, the wavelength inside the film, plus pi, and here we have to subtract the pi phase shift for the other one. So because both of them are reflection where the incident wave is in a medium that has a smaller index of refraction, so here let's say we have 1, let's say here maybe the glass is 1.5 and this is 1.2, the phase shifts at the interface don't do anything. They cancel out in the total phase difference between wave 1 and 2. So we're gonna end up with a phase difference that's just 2, let's write it as 4d, 4 pi d over lambda f. Now what is lambda f? The wavelength inside the medium. If the wavelength in vacuum is lambda, well, we know the speed is going down, right? And we know the frequency is not changing. So that's something we discussed before when we were talking about the rope. The frequency is just a property of the source. It doesn't change as you go across different media. So if the speed goes down by a factor of nf, right, lambda gets smaller. It gets divided by nf. So let's do the math a bit more carefully. So we're saying lambda is c over f. Lambda film is v film over f, the frequency. And c over vf is nf, the index of refraction. So from here we find that Vf is c over nf. So this becomes c nf f, and c over f is lambda, so that's lambda over nf. Alright, so that's now nf 4 pi d over lambda. And now the interference, of course, happens in vacuum or air, in a medium where the wavelength is lambda. So here, we want this to be, let's say, 2m plus 1 times pi, right? If we want to get destructive interference. So the lesson is, in the case where Ng is larger than NF, then we should choose our thickness D to be, the pi's cancel out. It's gonna be 2m plus 1 over 4, 1 over nf times lambda. Okay, so m can be any integer, but physically, of course, it doesn't make sense for d to be a negative number, right? It's a length. So mathematically, even though any odd multiple of pi corresponds to the waves being out of phase, that wouldn't make sense. We want the positive thickness, so the smallest m we can have is 0 here. So let's say smallest thickness could be 1/4 NF lambda, right? And then maybe the next one would be 3 times that. So we can, if we engineer our thickness to be this number times the wavelength of the light, you can cancel out and kill the reflected light. So, of course, the thing is we can't really do it for, at least with just one film of thickness d. It's not going to work for all frequencies or all wavelength in the visible range. But you can pick your frequency. You can decide what frequencies you want to cancel. Or pick somewhere in the middle of the visible range or something like that. All right, so that's a good application. So notice that NG doesn't appear here, right? The answer, the thickness, is just a function of NF and lambda. But of course, we had the assumption that NG is larger than NF. So here at this second interface, we have a phase shift of pi. And if you're in a situation where NG is smaller than NF, now what happens? Now we can look at our phase shift. So we don't have this secondary pi, right? So then delta phi would be exactly the same thing, like 4 pi d over lambda f minus pi. Okay, so this pi won't be there. So this wave that gets reflected here does not get inverted, and it doesn't have a phase shift with respect to this wave that's incident upon this interface inside the film. Now that would give different results, right? So it actually gives the same results as the case of constructive interference if NG is larger than NF, right? So constructive interference would be, instead of being 2m plus 1 times pi, here you just have some number times 2 pi. So it's like you don't have that plus pi. But that's already included in this. So we're going to get some different results. Basically, constructive and destructive switch up depending on whether NG is larger than an F or smaller than an F. So the main discussion today is interference in higher dimensions, so 2 and 3 dimensions. In 2D and 3D. So we talked about the propagation of waves in higher dimensions, right? So we once you propagate with a constant speed in a higher dimensional medium, your wavefronts, instead of just being kind of points that move along a line, become circles in 2 dimensions, or become spheres in 3 dimensions. And then you have, again, these wavefronts that propagate away from the source, and basically at some given point the phase depends on the distance to the source. So all of these points on a given circle have the same phase. So for example, I can write, let's say, this wave as let's say d of r and t to be a of r, an amplitude that now has to decay with the distance, and the oscillatory part has a structure like this: k times r, the length of this vector from the source to the point I'm interested in, minus omega t plus some phase constant. So now this is our general phase, right? So the phase at a given position, which is described by some vector, right? If it's a 2-dimensional system, R has X and Y components. If it's a three-dimensional space, R has X, Y, and Z components. But the only thing that appears in the phase, because it has to do with the distance traveled, right, with how far from the source you've traveled, only depends on the length of this vector. So for example, in 2D, if you say R is X times the unit vector in the X direction plus Y times the unit vector in the J direction, right? So X, Y, I, J. So you have some point here. Say this length is X, that length is Y. Then R, the length is the square root of X squared plus Y squared. And in 3D, similarly, R is the square root of X squared plus Y squared plus Z squared. So any point in the three-dimensional space that's a distance R from the source will have the same phase. And similarly, we can talk about the phase kind of dominating the nature of the interference. So if, now imagine you have more than one source. So let's say you have two sources, source 1 and source 2. Well, at some point, let's say that's a distance R1 from this and a distance R2 from this. If the amplitudes could be different, because they depend on the distance, but if the phases are the same or differ by multiples of 2 pi, which makes again the sine and cosine, makes the sine function the same, then when one is up, the other one is up, and they add up constructively. You get maximum constructive interference. And if there's a phase difference that's pi plus a multiple, an integer multiple of 2 pi, which gives you an odd multiple, an odd integer multiple of pi, then the interference is destructive. They're out of phase. All right. And the phases, see, so there is some part that depends on omega t, and that's going to be the same because we look at the interference at the same time, similar to the one-dimensional case. So if you want to think about the change in the phase difference for the waves arriving at a given point from these two different sources, it's going to be k times, let's say, R1 minus R2 plus phi naught 1 minus phi naught 2. Right? So similar to the 1D case, there is one contribution to the phase difference that depends on the difference between the phase constants of the two sources. And there's a contribution that depends on the difference between distance traveled. So now these distances, instead of being along one straight line, can have different directions. But again, the only thing that matters is the length of the line connecting the source to the point where we're interested in finding the phase. So to get more intuition, let's look at a simulation to see what happens. So basically what we want to do is we know exactly what D1 and D2 are at a given point in space, and then we add them, and we want to understand the pattern that emerges as you add the waves that are emitted from these two different sources. All right, so here's a Phet simulation. So there are some different ways to visualize. You can have this seems like water waves, this seems like sound waves, it seems like some electromagnetic waves or something like that. So they're going to do the same thing. So we'll play with all of them a little bit. All right, so first let's just turn on one of these, right? So you have one source and you have these wavefronts that move away, these ripples that move away from the source and they keep going, right? So you see part of a circle and each of these circles grows. And the effect that the amplitude is going down as you move farther away, you can also see that in the sense that, you know, it's brighter close and that it moves away, kind of it becomes darker. So the color code really shows maybe the amplitude, not the amplitude, the displacement. The color shows the displacement, and if your amplitude at some point is smaller, then you have smaller displacements. All right, so now I want to do it in phase, so let's try to time it. So when one drop falls, I click this. Yeah, see, they're falling together. Now, I would have two sets of circles, right? And at every point in space and time, the displacement is the sum of the displacements, those two simple displacements that we understand, as they have these spherical or circular wavefronts that propagate away, and along any kind of radial direction, you have a sine function. So our goal is to better understand this pattern. Okay, so first let's review just one of these in a bit more detail. So if I just start this, we see these wavefronts, and then I can look also at the side view. So this is a view from the top, right? The side view looks at some cross section of that, right? And then you have these sine waves that propagate away. As you can see, the amplitude is going down here. We can maybe increase the frequency, so more faster. And then because the speed is constant, right? Lambda times f is the speed, so lambda goes down if you increase the frequency. Can make the amplitude a bit bigger. Can go back to the top view and you see the wavelength is shorter. These wavefronts are closer together. Lambda is basically the distance between the wavefronts. So from the side view, it's going to be the distance between these peaks. Can also do it with sound. Again, it's a very similar thing. It's just the color changes. So thinking about, yeah, side view for sound is that's a three-dimensional thing, right? So it propagates in three-dimensional space. And let's do these electric type signals. Again, that's three-dimensional. All right. Can think about a graph also, seeing both of them together, right? Along this line, that's what it looks like. Okay, so now let's go to the case of 2. I think maybe the green one has the best visibility, so let's work with that. All right, so I can start this and start that. And see, that's the pattern that emerges. So there are these lines, right, that seem to be darker. Kind of seems there's destructive type of interference there. And then there are these bright regions that propagate away. So this just comes from adding, let me turn off one of them, right? So that if I turn it off, I mean, the wave that originally got emitted is already here now. It's out of this window. We just see this one. So, and if I turn off this one, well, these wavefronts move away. It stopped generating new wavefronts. Now, what we see is really like this quantity added to that quantity, and it gives rise to a pattern. So it's a very well-defined problem that we want to address. And then we can play with the separation. So if you bring them closer, if I bring them very close, that's the type of pattern we get. I can move them farther apart. See, there's a more complex pattern. Then if we increase the distance even further, there is a more complex pattern that gets generated. So we want to get a better understanding of this. And in particular, we want to be able to identify the places where the interference is destructive. We're not going to get big waves, which seems to be along these lines, right? They're kind of darker. So we want to identify those places and also identify the places where kind of we find the biggest amplitude. So it seems right in the middle of them there is the bright spots that move kind of have a higher value. Let's take a look at the graph here as well. So that's one cross section. Another thing that's interesting is you see these are waves that propagate in three-dimensional space. So if I put a screen, what do we expect to see? Let's say I put a screen at the end here, right? So along these places it should stay relatively dark, and in the middle it should get dark and bright and dark and bright, and the maximum brightness should occur somewhere in the middle. So let's see if that's what we see. Yeah, see these regions, because not the waves from the two sources are interfering in a destructive way, so the electric field over here is going to be very small. So if you put a screen, you kind of view, so you don't see that flickering because probably the frequency is higher than what our eyes can distinguish. So we just see some bright region. Let's see if I use a different thing. Can we put a screen for sound? No. Okay, so we can't put a screen for sound or water waves. All right. So there's kind of another framework to think about these. So let's think about the wavefronts from the two sources. So here's a picture of source 1 and source 2. One is blue, one is green. And we just take a snapshot at some point in time, okay? And we see these wavefronts. So these are our peaks. So if you play the movie, each of these circles is growing because the peaks are moving away, and at some point a new peak gets generated. So a circle of radius 0 starts kind of from the source a little bit later and grows. And of course, right in the middle of these peaks, we have the troughs, right? So there we have, let's say, so these are the crests, and a trough is right in the middle, and it has, say, the largest negative displacement. So for concreteness, imagine we're thinking about ripples on the surface of the water. So each of them has these crests, and of course they're separated by the wavelength lambda, right? The wavelength lambda, as you go along any of these radial directions, the distance between consecutive crests is the wavelength. So we want to think about the points where we have constructive interference, so we get the largest oscillations, and the points where we have destructive interference and we get no oscillations, kind of They're dark spots if you're thinking about light, or they're places where the water doesn't move at all. It's just there's zero displacement. Or places where you won't hear any sound if you just try to detect the sound at that particular point. So, well, how do we see it, at least at this point in time? Well, if you have two crests crossing, right? So here I have, let's say, one blue circle and one green circle. Yeah, they add, and they're both positive. They have the largest value, so you're going to get the largest possible value. So let's think about the phase difference, right? So here you have a distance of lambda to the source. For this one, let's just focus on this one particular point. Let me make it smaller here and draw. So I want to focus on this one point here. From here to here, right, the distance to this source is 2 lambda. It's on the second circle of radius lambda around this source. And from here to here, the distance is lambda. So now we can think about the difference in phase, right? So for that one particular point, delta r, the difference between distances, is 2 lambda minus lambda, and that's lambda. And therefore the phase difference, which is 2 pi over lambda times delta r, is 2 pi. So there is no phase difference. You know, even at later times, right, they may not be at their maximum value, but at that point, the interference will be constructive. So always, even if, like, when these waves propagate and the wavefront moves a little bit away, both of them will have the same positive value. So they're always in phase at those points, because the phase shift just depends on the difference between distance traveled. The sources are in phase, right? Because if you look at one snapshot, both of these crests, the first one, are the same distance from the source. So it means they're producing oscillations in phase. So the only thing that contributes to the phase difference is the difference between distance traveled, and that's the difference between the radii of the circles if you look at the points on these circles. Therefore, you see, for all of these points on this line, so I pick this point. Now here I add to this lambda, to this 2 lambda rather, I add another lambda. So this distance for this other one becomes 3 lambda to this, but it also goes on a bigger circle of radius 2 lambda. So again, delta r is lambda for this point. And the points in between, right? So you can imagine maybe a circle of 2.5 lambda in the middle of them, and a circle of 1.5 lambda in the middle of these two. Again, all the points in between. So there's going to be all that line where the interference is constructive. The two waves always add up with the same displacement. Now, interestingly, there are these points where the interference is destructive. So if you have a crest that's a positive value, right? So thinking about here, sorry, I need to make it smaller to draw. Let's go to black here. Okay, so here you have some maximum. Right, so if you think about the displacement along some cross section, it's maximum at the source, it's minimum in the middle of the source and this crest. So there's a trough here, there's another trough here, there's a crest here, there's a trough here, and this is a crest. So in the middle, we have the troughs, right? So if you think about, let's say, this point here, it's on a trough for the waves coming from the blue source, and it's on a crest for the waves coming from the green source. So something like this, you have a peak and you have a minimum. So they're gonna interfere destructively and annihilate each other. So along these lines now, we have dark spots. We get destructive interference. Okay, so again, how do we know the condition? As we mentioned, we just have to think about the phase difference. The phase difference has two contributions. One is from the difference between length traveled to reach each of the sources, and there's another one from just the difference between the phase constants of the two sources. And if that difference is an integer multiple of 2 pi, then we get maximum constructive interference. If that's pi plus an integer multiple of 2 pi, they're out of phase, we get destructive interference. So here's an example. Let's think about various points. So we have a bunch of points here. We have 3 points A, B, and C, right? These are the sources. This is a snapshot. We see the picture of the crests. So we want to figure out what kind of interference we have at points A, B, and C. Okay, so thinking about point A, it's a distance 2 lambda from the blue source. It's on the second circle here. And it's a distance 3 lambda from the green source. So the difference between distances is lambda, and the sources are in phase. Here, the initial sources that are in phase. So that's a point of constructive interference. And you can see it's on 2 crests. So at that snapshot, at least, it has an amplitude that's twice. Well, that's the sum of those amplitudes. Yeah, unlike the 1D case, the amplitude is not constant for each of the sources. You move away, the amplitude for the crests can decay. But both of them, their maximum values get added together to give the displacement here. Point B is a distance 3 lambda from the green source, 2.5 lambda, right? It's between 2 and 3. So now the difference is half a lambda. Half a lambda divided by lambda times 2 pi gives pi, right? It's a phase difference of pi. So basically any lambda doesn't change the phase difference. It gives a phase difference of 2 pi, which is nothing. But any half lambda can make you completely out of phase, because it gives a phase difference of pi, and then adding a pi to a sine function makes it gives it a negative overall sign. So B is a point of destructive interference. What about point C? So C is half a lambda from the green one, and it seems to be 2.5 lambda from the blue one. So 2.5 minus half is 2. So it's a 2 lambda path difference. So that's a 4 pi phase difference, which is a multiple of 2 pi. It doesn't change. So they're in phase. They have constructive interference. Now, we did this exercise for a bunch of individual points. Now you can try to find like all points in space, right? Or on this plane where the difference in the path traveled is a fixed number. Okay, so for example, these are two sources again. So here the differences are, this is a line, these are all the points that are the same distance from the sources. Here that's lambda. Here, depending on how you define it, you can also say the ones on this side are like minus lambda, right? If you say it's R1 minus R2, this and this, these are different nodal, these are different values of delta R. But if you just take the absolute value, so that's lambda, and then you have 2 lambda. So the separation between two sources is 2 lambda, right? These circles of radius lambda are touching at this point. So if you think about one point over here, what is the difference between distances to this and that? It's going to be the distance between the two sources, which is 2 lambda. And then for other values, we're going to get these curves. Again, we can construct a whole bunch of those points and connect them, right? We can, yeah, find all the places where two crests overlap, like here, 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 and to each of them kind of assign the value of delta R, and the ones that have the same delta R, we connect them with these lines. And so the ones where delta R is some multiple of lambda, they give maximum constructive interference. They're also known as antinodal lines. They're going to be the brightest areas. And then the ones where you have a crest and a trough, so the trough is going to be halfway between two of these. So for example, a point here, right, is on a green circle, it's halfway between two blue circles, so it's on a trough corresponding to the blue source, it's on a crest corresponding to the green source. So it's delta R is some odd multiple of lambda over 2, and that's the place where the two waves are out of phase and they give dark spots, right? They interfere destructively. Okay, so here's an exercise, quick question. So read this and try to find the answer, and then we come back and go over it together. All right, so we have two in-phase sources. They emit sound waves of equal wavelength and intensity. So at the position of the dot, what is the interference? Is it destructive, constructive, somewhere in between, or we cannot tell? All right, so it seems that it's halfway between the two green crests. So it's a distance 1.5 lambda from the top source. And it's also between the second and third crest corresponding to the bottom source. So it's 2.5 lambda from the bottom source. So 1.5 minus 2.5 is minus 1. So yeah, the delta R, if you forget about the sign, is just lambda, right? So that must be constructive interference. Yeah, this is 1.5, this is 2.5. Delta R is lambda. Therefore, the phase difference is just 2 pi. Here's another one. So again, pause the video, try to find the answer. Okay, so we have two in-phase sources. How many antinodal lines of constructive interference are in the interference pattern? Okay, so how can we find them? Well, there's going to be a horizontal line here going through going through these points, right circles of the same radius crossing, so that's also by symmetry. All the points on this line perpendicular to the line connecting them going through the middle is going to be the same distance. So here we have delta r is 0. Then we can have maybe the first from the green crossing the second from, or yeah, the first green crossing the second blue, so it's something like this. And then the second green crossing the third blue, third green, fourth blue, something like that. So connecting them, something like this. So this, depending on the sign, this is just lambda. And we don't seem to have more crossings. So for example, can we have something that has a path length difference that's 2 lambda? So we would want maybe the first green crossing the third blue, but that doesn't happen, right? This circle and that don't cross. So then there's going to be another one also on this side. Again, it's lambda with a different sign. So in one case it's R1 minus R2, in the other case it's R2 minus R1. But yeah, that's basically the answer. We have 3 antinodal lines. All right, let's stop here. So you will get quite a bit more experience playing with these figures in the lab this week. And we'll continue this discussion in the next lecture.